In this series of lectures, we introduce some basic and important concepts in calculus. As an entry-level course, we often adopt approaches that are intuitively clear, but might not be mathematically rigorous. In particular, we will not use the famous epsilon delta language. In this lecture, we'll look at something called the mean value theorem. Okay, so first let's look at what is the mean value theorem. Suppose I have a function which is continuous within the closed interval from a to b, and it's differentiable in this open interval ab. Now let's look at two endpoint, which is look at the right one. So this is the b and fb, and this is the left one, a and fa. Okay, now we connect these 2 points to get a line. So now I look at the line, then I connect in these 2 points. From coordinate geometry, we know the slope of this line. If we look at the slope of the line, is calculated by the quotient between the y difference and the x difference. Okay, so this is the slope of the line. All right, now if we move the line up parallelly, we move the line. And then intuitively, it's kind of clear. If I move the line parallel, that at some point, it's going to tangent to the graph of the f. Okay, so let's say this point is x0. Okay, so the line, after we parallelly move it, the line tangent to the graph of the function at point x0. Now, because it's parallel, the slope is the same. So slope is the same as this, is fa minus fa and b minus a. And this tells us, and the assumption that f is continuous and differentiable ab, then we can always find a point x0, which is between a and b, such that the derivative, right? So we know, okay, so this is because it's the slope, right? Slope is calculated by the derivative at this point. That's the geometrical meaning of the derivative. Okay, so we can always find a point such that derivative at that point equals to fb minus fa divided by b minus a. So intuitively, everything is clear. Okay, now let's rigorously prove this mean value theorem because it's very important. All right, so let's do the rigorous proof. Intuitive is clear. So what I'm going to do is we're going to do rigorous proof. Okay, in order to do that, as step one, let's first look at special case if fa equals fb. So fa and fb, they're the same. That means if you connect these 2 points, it's a horizontal. So let's say they equals to a number, which we denote as m. All right, so then what do we need to do? We need to show that there exists a point x0 between a and b such that the derivative equals 0, because in this special case, we assume fb and fa, they are the same. All right, so how should we do that? Let's look at 2 cases. So case 1, if the function fx is constant, right? So if the function is constant, that means it's equals to this n, right? So for all x belongs to ab. Now, if that's the case, we know if your function is constant, then of course we could get the derivative, it's everywhere 0, right? So we just get, okay, we get the derivative 0. This is for all x belongs to a and b, then everything, it's obvious, right? Okay, so that means the graph from a to b, the function is constant. So the derivative is 0. Now let's look at case 2. What if not? Which is more general, right? We say, okay, in general, of course, the function is not constant. So let's say if the function fx is not constant, then what? Okay, if it's not constant means we have, if I look at the maximum value of the function fx, right? So look at between ab, I have this one is bigger than n. Okay, what is n? N is the value of fa and fb, right? Okay. We have maximum is bigger than this, or we have the minimum value of fx, this is less than n, or both, right? And the point is at least one of the two. Okay, let's say, suppose, okay, at least one of the two, suppose this is correct, right? Then we say, okay, let's assume this one is, according to the extreme value theorem, we know if the function is continuous, then you can always find a point such that the maximum, the function has maximum, attains maximum at that point, right? At x0. Okay, so this is the maximum value. All right, and then we know by Fermat's theorem, then we say okay by Fermat's theorem. Okay, so if the function attains maximum or minimum at the point, then we say, okay, we just get the derivative of x0 equals 0, right? So this is something we discussed before. Now, geometry, of course, is also clear. That means the tangent line is horizontal, right? So it's okay. We have the derivative of this one is 0. Okay, so then we are done. All right, so the point is here, we have rigorously established the mean value theorem for the special case if FA and FB, they are the same. Now, let's look at a more general case. If they are not the same, right? So this is the general case. Now, if they are not the same, what do we do? All right, so what we do is we are just look at the line. We say, okay, again, we just connect the two endpoints and we look at the equation of the line. So this is the slope, right? So this is the slope of the line. And then we look at equation. If we write the equation, it passes to the point FA, and it's with the slope. So this is the equation of the line, right? So this is the equation of the line. And we look at the difference of the function and this line. So this is, we just write out. Okay, so I just look at the difference between these two, right? The difference between the function and the line connecting the linear function, connecting these two endpoints. Now, let's look at the difference. What can we say? Of course, the function is also continuous because it's difference of two continuous functions, and it's also differentiable. It's just a difference of two differentiable functions. But more importantly, if I evaluate the function at two endpoints equals 0, let's say say y. All right, let's check this. Okay, let's check this. So what is GA? GA is still G will be FA minus FA, and then plus when x equals a, which is 0. Okay, so it's FA minus FA, which is 0. All right, and let's check what is GB, right? So GB will be FB minus, this is FA, and plus K, and B minus A. But remember, what is K? K is this. If I put a K right here, and this guy will just be FB minus FA. So everything will just be canceled. So this is also 0. All right. So now the point is, now I have a function which is gx, right? And the gx equals 0 at these two endpoints, right? So it's gb equals ga equals 0. Now this goes to what? This goes to step 1, because step 1 says, all right, so this is we already showed, right? If I have these two things the same, then there's a point between them that due to 0. All right, so by step 1 implies there exists, right? So okay, so there exists the point x0, which is between A and B. And so this means there exists, right? So okay, so there exists, let's say this is point x0 between A and B, and such that, right? Such that, okay, so we say, okay, so such that the derivative of gx0 equals 0. So this is from what? This is from step 1. Now, what's the derivative of gx? Right, so this is gx, it's right here. All right, so what's the derivative? If I want to calculate the derivative, right? So, okay, what is the derivative? The derivative of gx, g prime x, is equals the derivative of fx minus the derivative of lx, and then you see it's just fx minus k, right? It's just fx minus k, because this is constant, this is linear function. You take the derivative, just get a k. All right, and from here, then you see this just tells us there exists x0 belongs to AB, and such that now I plug into here, so it's f prime x0 equals k. But what is k? K is the slope, right, of this line segment, this line connecting the two endpoints. Okay, so equals to FB minus FA over B minus A. We are done.